No, I literally asked.
All right.
Nobody can contain the beast inside.
Okay. So let's talk a little bit about that lab from yesterday. So basically, you had two different systems. You had an open-closed system, and you had one open system, okay? So we model it like this. In reality, these are actually compression waves, okay? But mathematically and visually, it makes it easy to see if you draw it as a transverse wave. In reality, it's not. So here's the whole point on these open-closed systems. When you measure that height, what you were measuring was 1/4 of the wavelength, okay? And that's going to be like that first harmonic. So what's happening is that sound wave is being sent down, it's bouncing off the water, and then when you hit just the right point, that's when it got really loud. That's when that wave was reinforcing itself, okay? And you had constructive interference. So that wave was basically matching itself like an evil twin. So it was like, ooh, let's catch you on the way up. But it had to be in phase. That's when it got really, really loud. So when that happened, you have 1/4 of that. So what you did is, and you had to do with that correction factor of 0.3 D. So that together allowed you to get the wavelength. Then you knew the wavelength, you knew what the frequency was, you calculated the speed of sound, okay? So again, on that second page here, I don't need to see all 3 trials of calculations, but I clearly want to see one set of calculations, okay? I don't need to see them all, but I better be able to see one of them very nicely labeled, know exactly what you're doing, okay? Keep that in mind. Now, the other one, which was that open system, and that's harder to get it to really resonate, mainly because of the fact that on that open-closed system, it's just bouncing off of water and it's coming back. This, you're making the entire column resonate, and so you can hear it, but it isn't as distinctive as that open-closed system is. So, but with this one, because this is representing half the wavelength, so again, that distance on that open system should have been somewhere between 0.3 and 0.4 meters, okay? When you heard that. And then it's the same process. If that's half your wavelength, to get your entire wavelength, you multiply that by 2, you're off to the races, boom, there you go. Okay? Cool with that one. On the unknown frequency, on that one, the only thing that I can grade is your process. Okay? So make sure that you show me all the steps, and you need to take that 0.3 times diameter as part of that correction factor into those calculations. Okay? So some of you wanted to know what the actual one was. It's actually 440. So that was the actual frequency of the tuning fork. Typically, you get pretty close to that value.
440 A concert.
What'd you get?
No, 440 is concert A. It's like when you hear the symphonies and they all tune, they tune to that frequency. Nerd.
Yeah, that's kind of a nerdy thing. Okay, so when you get to that free response question, so let's talk about that one. So basically, you have an oscillator and you have a weight hanging from the end of the string. Now, here's the story. 4 strings are set upside down, B string is the same, and the mass of each block is the same. So because the mass of each block on the end is the same, what do you know about the tension in the string? They're the same, because you have the same block hanging from the end of that string. So they actually gave you this equation that V equals the square root of your tension M over L. You all are used to seeing that as force tension divided by mu. It's the exact same equation, okay? It's the exact same thing. It's just they put it in terms of M over L. It still works. So when you look at this, and here's your thought process. What's the same for all of them? For all 4 of them, what's the same? There's 2 things that are the same.
The tension.
The tension and the
Length.
length. Okay, that's the same for all 4 strings. Okay, that's the same for all 4, the force and the length. So what's the only difference that can exist? The mass per unit length, otherwise known as the size of the string. Okay? Now,
I know, but isn't that the same?
since that's underneath the radical, could it be a linear function? No, because it's underneath the radical.
Doesn't say the mass of the string.
When you get to that last diagram, yes, there's a backside to the lab. So this is more a function of terminology. So here's your oscillator, and it says on this one it's the second harmonic. So if you don't know what the second harmonic looks like, you really can't draw this. So your first harmonic would be something like this. Okay, that's as simple as it possibly can get with a standing wave. Okay, that's as simple as it gets. That's the first harmonic.
Art club, musical club, please go to the small gym for your group pictures. Eagle Theater, Art Club, and Nintendo Club. Please go to the small gym for your group pictures.
Why did you look at me like I was?
Now, if it's the first fundamental, how many nodes and antinodes do you have?
2 nodes.
2 nodes,
One antinode.
1 antinode. Okay?
I can count to
Because remember, Lauren, what's the velocity at the nodes? 0, because those are your anchors. Those points aren't moving, okay? It's your antinodes where you have your big vibrations, okay? So if it's the second fundamental, this is going to look like this,
Wasn't done.
okay? Now, how many antinodes do you have? 2. How many nodes do you have? 3. So notice that you always have 1 more.
Node than antinode.
Dang it, this isn't it. I actually folded up my graph paper, and I thought that was it, but it's not it. Oh wait, yes it is. Yes it is, we're good.
So help me God, you hand that in. That's what I'm going to do to your entire lab. Okay, I'm just telling you now.
You won't be able to tell.
Hide and watch. Okay. So once you get that, then that question becomes pretty easy to answer. Okay? All right. Make sure on the graph.
Danny, you're right.
On the graph, what are you going to graph on the y-axis? Frequency. And you're going to graph 1 over wavelength here. So when you do this, and you do change in y over change in x, what units do you get?
Velocity.
Velocity.
Wow.
Because that's 1 over seconds divided by 1 over meters. So what's going to happen? It flips up, you get meters per second. There you go.
That's called.
Okay? All right. Are we good on the lab? So staple the graph, Cohen, neatly drawn to the back and get that handed down.
You want the graph first or the this thing first?
What order?
I want the paper, the FRQ, and then the graph.
This is perfect.
Cohen.
It's, don't worry, this one, it was actually, I had the greatest vertical speed.
Oh my god.
I don't know if you're supposed to be like,
Where's it moving up and down the fastest?
or like what the heck?
You need like
This is a good move from yesterday already
actual
gone.
dictionary of things to call Cohen.
It's the anti-nodes.
The mode stuff. The nodes don't move.
Oh my god, no.
Hey, can I see your graph? Can I see your graph? Oh,
I don't know, but you're right. It's only Tuesday. We gotta log in.
Only one more day.
is this the graph of time? Is this the graph of time?
Okay, wait, the graph.
Oh, really? What about this? Oh, wait, no, never mind. That's just awesome. Okay. Wait, we're both in the, you two are in the middle of the same group. What am I gonna do?
Honestly, I probably should change this to where
In the graph. No, the lab.
flips, but honestly, I really don't
Well, I
feel
think if you do the lab, we go on top. But
it's technically, those are also
And this is what I told Cohen. I swear to God, if your grade comes down to 1
every
point,
point matters.
I will give that back to you. But right now, no.
Thank you.
What about my point?
It makes sense.
I swear.
Why didn't you just draw it twice as big?
I didn't want to. Yeah, I wrote the 2 down. And I was like, this is perfect.
How'd that work for you?
Okay, so
Okay,
Read it. It says it on the front. We just went over this.
what?
The slope.
In sync.
What's the slope gonna get you?
speed of sound, right?
No, yes. Which is
oh, so
which is what? What units?
because it's the
There you go.
Okay, got it.
Wait, so put that in.
Okay.
That's the inverse. Yeah.
Okay, anyway, back to our story. All right, Danny, fire up that camera.
Oh, it's been running.
Okay, it's been running, fantastic. Okay, so here's the last thing that we're gonna cover today. This is a very brief introduction into light, okay? Just like the beginnings of this. We're gonna spend the entire next unit on optics and lenses and mirrors and everything. So it's odd, so this test is actually gonna cover like chapter 15, a little bit of 16, and a little bit of 17, okay? So it's gonna be kind of a hodgepodge of stuff, but it's all related to waves and all this stuff. So when you look at light, one of the great debates that happened in terms of what is the nature of light is that you had kind of 3 different ideas. You had the wave theory, you had the ray theory, and then you ended up with what's called the wave-particle duality. And depending upon how you observe light, you can make an argument for all 3. So what I'm going to show you first is actually, it's called the double slit experiment. It's relating to photons and electrons, but you're going to get the visual of what a wave-particle duality system looks like. So it's a little hokey, but it's not bad. So bear with me. Let me get that fired up. It is. It's a little hokey. I'm not going to lie. But it very much gets the point across.
Bro, You're gonna hokey my pokey? What? That is on the video now. I don't care. I've said so many things on video. You've said. I don't care.
Please, can we put him on the spot?
Dude, the Hokies. Virginia Tech. No, I'm saying in general. Hokey to pokey, quick physics. For a Hokey sandwich, you understand? Hokey, stupid. That's on video. You can't do that. Can't hear what?
Charles.
So say it again, louder.
That's why, yeah, that's what I said.
So it doesn't
Hey,
matter.
what?
Pretty sure.
I already said it. I know, I said it first. No, you didn't. I said it louder and more funny. You're also watching it now. I don't make up any of my own stuff. It's all made up. I just say it loud.
Yeah, but I usually say,
Yeah, you actually just stole his joke earlier. Like, Owen laughed at it. I just said it louder and funnier.
No, I didn't think that
Sorry, I'm
would
so
work.
funny. No, quit stealing my joke. You both just read it.
Okay,
Wait, does that say?
so I'll stop this along the way, but it's actually, like I said, it's a little hokey, but it very much gets the point across.
Oh.
Here we
Whoa.
are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right.
So this is what
Now,
particles look like,
look
if a
at
double
waves.
slit experiment.
The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the
So that's
marbles
gonna be
make.
like a maximum.
But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out.
That's destructive
So
interference.
now, there is an interference pattern on the back wall. Places
So if
where the
they're
two top
waves,
are the highest
remember that
intensity.
visual. That's the
Right.
pattern you're gonna get if it's waves in a double slit experiment.
So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons.
So this was one of the most mind-boggling events that happened in quantum mechanics. Because this was done in the 1920s, early 1930s. And so everybody was convinced that the electron had a certain mass, it had a certain charge. It's a bit of matter, okay? And so these were all physicists, and they said, oh, the electron is gonna be orbiting the nucleus like planets orbit the sun. And in their mind, when you shot these particles on here, because it was matter, it should create just the two bands on either side, because it has mass. It has a certain charge to it. It should not behave like a wave.
Tiny bits of matter through. And we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere.
So again, this is one at a time,
But
not
after
groups
an
of
hour
them,
this,
one
the
at a
same
time.
interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by
That eye is
to
kind of creepy.
see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an
So if you,
interference
it's
pattern
called
of
collapsing the wave function.
The
So if
very
you collapse the wave
act of
function,
measuring
basically you force the electron
observing
to choose
which
one state or
slit
the
it
other.
went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched.
It's kind of creepy.
Here that physicists step forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay.
Well, that's fun.
So,
Watching it, you don't want it. No, if you're watching too, you don't want
So you no longer.
the electron knows it's supposed to collapse. We don't.
That's how it works.
That's how it works. That's how it works. No one can quantum.
Okay, now, come back.
How it has to be active on computers.
Electrons.
That's the problem.
Yeah.